Good morning, everyone. Today we'll first discuss two or three more examples on dynamic programming. Then we'll start our discussion of the theory of NP completeness. All right, so let's start with the following problem, a weighted interval scheduling problem. Actually, we have seen it earlier when we discussed the grid method. So what we have is n intervals. So each interval has starting time and finish time. So each interval is specified by its starting time and finish time. We can assume that intervals are ordered with respect to their finish time. Otherwise, we can sort them, right? That's quite easy. When we discuss grid methods, we discussed how to choose a maximum set of mutually compatible intervals. So we know how to solve it using grid method. Now the problem is getting more complicated. If we not only want to maximize the size of intervals, the number of intervals that can be scheduled for, say, a resource. All right. Actually, we want to not just to want we not only want to maximize size of the intervals we chosen. Rather, we want to maximize the the sum of their weight. So the objective function now is different. Originally, when we discussed grid method, we just want to maximize the size of set we chosen. So we can use the grid method. So that can be solved by grid method. So we know how to do it. Now the objective function is different. We want to maximize the total weight of these intervals. Now each interval will give it a weight. For example, a trivial example, of course, the weight Wi is just length of interval. That's the most natural one. So then the problem related to the efficiency of scheduling. Originally, the efficiency is just to maximize the activities that can be held, say, in a classroom. But the problem is some activity takes a short amount of time. So from the classroom perspective, it's not efficient. It's not cost effective. So we want to schedule activities so that the efficiency of the classroom is maximized. So in this regard, we can put a weight function on it. For example, weight is just the length of each interval. Of course, it can be something else. So weight. Perhaps each activity involves number of persons. So it can be number of students involved. All right. Or it can be combine these two together. So number of students involved. Say let's just put this number, say times Fi minus Si. It can be anything, whatever you think is a reasonable measure. All right. So each interval will have a weight. Now our objective is to maximize total weight of activities that can be scheduled for this given classroom. So these activities are mutually compatible. So that's our task. Grid method certainly does not work because of the weight function. All right. So how can we solve this problem? So let's start with an example, maybe. Okay, so for example, look at this example. So we have 8 different activities. If we want to choose maximum set of activity, you can easily see there are two two answers at least. I think it's just two answers, each with 4 intervals. If we maximize the size, if maximize number of chosen intervals, so that can be 4, right? I think it's easy to see two possible solutions. One is this one. Maybe let me use tick. This 1, 2, 3, 4. So another one will be 1, 2, 3, 4. All right. So it's easy to obtain one of these two solutions by using greedy method. Now the difference is each activity has a weight. Each interval has a weight. So let me try to put a weight in. Okay, I think that's good enough. All right. Now our objective is to maximize the weight of intervals that we chosen. So again, this set of intervals are mutually compatible. All right. So if you look at the two solution of maximum size, so one is this one. So that will give us total weight 19. Another one is this one of size 4. Just give weight 11. All right. So if we want to maximize size and also maximum weight, so among mutually compatible activities of maximum size, we want to maximize its weight. Then this one would be a solution. So 19. All right. But now if we don't care about size, but what we really want, yeah, at 712, you already see the solution. Actually, if we want to maximize total weight, then actually I think it's a unique solution here. It's a unique solution, which is, let me use, I still use red one. This one plus this one give us 21 instead. All right. So this one also shows greedy method does not work. So greedy does not work. It does not work. Because greedy will choose the interval, will choose a set of interval of size 4, but this optimal solution only has size 3. All right. So how can we solve this problem? One way is to use dynamic programming. So how can we use dynamic programming to solve this problem? Let's take a look to see the properties in connection with this task, what we need, right? So let's see. So let's take a look. So suppose we choose let's consider particular activity. So let's highlight it, maybe just this particular activity. Okay. Let's consider this particular activity. Say I, stop. All right. Now consider our solution. Eventually say S is our solution. So consider this activity with respect to our solution. So there are only two possibilities, right? Either I belong to our solution or this one does not belong to our solution. And recall our dynamic programming algorithm for subset sum. So actually that one can be used as a template for many problems that can be solved by dynamic programming. For example, a CL1 knapsack problem, which I will not discuss in class. In textbooks, there are two versions. Please read these two algorithms. That's very important. Again, I emphasize that's very important. Knapsack problem. As a textbook, one section discuss two different versions. But it's basically using ideal subset sum. Okay, same idea. All right. Okay. So we will not discuss in class. for knapsack. So only two possibilities. Either I star belong to sub S, another one is does not belong to S. So if it does not belong to S, what do we do? If it doesn't belong to S, what do we do? All right. So one important thing is to identify sub-problems. So here, the nice thing about this activity selection is intervals are ordered. We have this ordering already. So this naturally gives us a way of defining sub-problems. Sub-problem may be choosing from solution. Okay. Yeah, the pen does not work very well. The optimal solution for the first k intervals. So that's naturally define sub-problems. So if we have that in our mind, for subset same thing, we define orderings, then we can talk about first numbers, right? Okay, so if we have that in mind, then suppose this I star belong to S. Maybe easier is it does not belong to S. So consider second case, that's easier case. If this one does not belong to S, let's see, which one? No, sorry. I better discuss first one to illustrate one idea first before going to this one. Sorry, I go back. Okay, maybe it's better to discuss. Sorry, I changed my mind. Starting with this one first, because I want to see optimal substructure or optimal structure. All right. Suppose S star is in the solution, so we do choose this one. Then what happens? So once we choose this one, automatically interval not compatible with Si star will be taken out. So this one will be out. This one will be out. Then, and also this one will be out. Then for the remaining intervals, now consider solution for remaining intervals. What can we say about this? So solution for remaining intervals, any optimal solution for the original problem can be obtained by optimal solution for remaining intervals plus I star, if I star is in the solution, right? So that's optimal substructure. So because this one, that suggests dynamic programming work. So here what we need is optimal solution for remaining intervals. Once we obtain that, we just add I star, then we get an optimal solution for the original set of intervals. So and the assumption is I star belong to solution. So you see, we reduce the problem to a smaller set of intervals. And we have a recurrence relation here. All right. Now, of course, this is an assumption that I star belong to S, which we don't know at all, actually. All right. So that's why we need to consider another case that I star does not belong to S, because we don't know which one happens. All right. But anyway, if I star belong to solution, then that's what we have. So we only need to find optimal solution for the remaining intervals. Now, under our consideration is that we're looking for interval solution for first k interval. That's our sub-problem or sub-instance. Then we don't need to care about intervals coming after the interval I star. So this part, actually, we don't need to care. We only need to look at interval before it. So we only need to look at interval here. All right. So what we need to do is find the optimal solution here for these intervals. So that's now you see dynamic programming comes in, actually, the bottom-up approach. So we solve smaller problems. if we just want to solve it for optimal solution for remaining intervals, that's not a subproblem. See, you can think, you can regard this one as a subproblem, but this one is not well organized. It's a kind of messy. We don't know how to do subproblem in this way, starting from smaller subproblem to larger problems. But the green one, we know how to do it. So from left to right. All right. So that's what we are going to do. So let me erase the red part. We don't need this one. So we don't really need this part. We don't care. All right. So green one. All right. So in this case, what happens is, so let's define the value. So let's define the value. Say OPTI So OPTI denotes optimal value for first I solution. So value of optimal solution for first I intervals. So what we need to do is optimal value is OPTN. That's what we want. All right. So for the first case, what can we see is optimal solution will be optimal solution of the green part plus weight of this I star. Right? Because we know I star is in the solution. So that's what we get. So what's the optimal solution of green part? So we need to introduce another notation called R of I. That's rightmost interval. Within first Ki intervals. With the ith interval, with I. So notation a little bit different from notes, I think. I use I as interval I. Here I use I. All right. Now, look at all intervals that come earlier than I star. So some are not compatible. So for the non-compatible intervals, we don't need to consider them. So this one is closed. Yeah, elements are important. They're sorted. Okay. Yeah, it's very important. All intervals are sorted with respect to their finish time. It's essential. All right. So this one is rightmost. All right. So the green part is just optimal one of Ri plus weight of I. So I star says ith interval. If this ith interval, so we have this relation. Okay. So first case we know how to do it. And second case is even easier. If it's not inside, so then the second case. So first case I erase them. Okay, so we all know how to do it. Erase them. Second case is this one is not in solution. So this one not in solution. All right. So if it's not in solution, what do we do? It's very easy. So if not in solution, then we just consider the green part is here. Sorry, the green part is here. All right. So in this case, what we get is optimal I minus 1. So for this case. So putting them together, then we have the following reconciliation. Optimal value of the first ith interval equals maximum of two possibilities. One is it's not it's a solution. I think we did that one first. So it's maximum of OPT, rightmost one, compatible with the ith interval plus the weight, and then this one, I minus 1. So that's the translation we obtain. For R of I, the boundary condition is, if it does not exist, then Ri equals 0. Okay. If green part is empty, then that's what happens. If no such interval, okay. That's boundary condition. Be careful with boundary condition. It's a trivial part. It's a very easy part, but that's a place you really need to be careful. Very often, that's a place causes a huge problem when you implement it. The trivial part. Very often, the trivial part will cause you headache if you do not set it properly. All right. So anyway, we can easily obtain this reconciliation. So once we have this one, it's obvious how we compute it from left to right. Total time will be, so we do it n times. Each time, because of computation of this one, the rightmost index. So total time, say, n squared. All right, we can easily do it. Eventually, it's filling a table from left to right, one-dimensional table here. For subset sum, we fill a two-dimensional table. Typically, dynamic programming should fill a table. The dimensional table depends on the number of arguments involved. For subset sum, there are two arguments. Tij, I think in subset sum, we have Tij. So it's a two-dimensional table. All right. So here it's one-dimensional. It's very simple. All right. Is it clear how it's done by using dynamic programming? Again, the key point is the problem has the optimal substructure. Therefore, we can use dynamic program to solve it. Okay. All right. So actually, last week I said if I do it quickly, I can finish two examples in 15 minutes. If I do slowly 30 minutes, I guess I'm even slower. Okay. I'm giving you a lot of detail here. Perhaps I will spend the first class just for these two examples, but it's okay. We have time. All right. So I do have luxury to give you enough details to convey the idea involved, the process. I show you the whole process. All right. So it's quite easy, right? I'm not sure if it can be done in log n. It seems to be difficult because of this one. Because of finding this one, I haven't really thought into details. How can we find the rightmost interval that's compatible to interval II? If we can do it in log n times, then it can be done in log n and log n time. Okay, but very nice thought. All right, so you can try it to see whether it's possible. It may be, I don't know. I really haven't thought too much about this one. All right. Yeah, but maybe binary search will work in this case. Okay, so I'll leave it to you to figure it out. Okay, because my main focus here is not the running time itself, but rather the idea of dynamic programming. So here, because the interval sorted already, so maybe log n will be good enough. So it's possible maybe at log n. Okay. Okay. I leave it. Maybe I leave it as homework. Okay. All right. Now, there's an interesting connection between this problem and some important concepts in graph theory, which I want to introduce, because when we discuss NP completeness, a lot of graph problems will come in, and these concepts are very important and play essential roles. So before I discuss next example, I want to discuss a little bit on such connection. All right. So three main concepts. I want to do a very quick review. There are three very important concepts in graph theory. One is called the complete graph, that is clique. Another one is independent set. Some people also call the stable set, but nowadays most people use independent set. In older times, actually very often it's called a stable set. And also vertex cover, these three notions. Vertex cover, all right. So these three important concepts in graph theory. A subset of vertices, so we have a graph G, undirected graph. All right, then a subset of vertices is called a clique if it's a complete graph. If it's induced subgraph, if this one induces a complete graph, so contain all possible edges, that's called a clique. And okay, and the independent set means this one has no edge. Just a set of isolated vertices, that's called the independent set. And vertex cover is a vertex cover. These three notions are extremely important. You must remember all these three notions if it covers all edges. All right, an edge is covered by its end vertex. For example, if I choose this vertex, this will cover this edge. All right, so let me draw a picture of what it means. All right, so in this picture, V prime is the vertex cover. So all edges of the graph is on either cross edges or on V prime side. So this side has no edge. So this side has no edge at all when V prime is vertex cover. So that means this side is independent set. All right, so what this means is V prime is a vertex cover if only if the complementar set is an independent set. So they have this complementary relation. All right. Now the relation between clique and the independent set is also very close. That is in its complement graph is a clique in G if only if in its complement graph. Because in the complement graph, no edge become edges, edge become no edges. Okay. So let's take a look. I'll give you a small example. So in this graph, this one is a 4 clique. Now in its complement graph, so number of same set of vertices but the edge become no edge become edges. So we have this edge, this one is edge, this one is an edge, this one edge, this one is an edge. All right, I think that's it. Okay, so it's this graph G, this is complement graph, G prime. Now here click become independent set. So here four vertices have no edge at all. It's edgeless graph. So there's such a relation. In other words, when V prime is vertex cover, then V minus V prime is a complete graph, is a clique in its complement graph. All right. So these three concepts are really tied together. So in terms of solving them, if we can solve one problem, we can solve the other two. Same thing, basically same problem, but look at different point of view. All right. So that's very quick review. Oh, that's for this one. This one is a vertex cover. It's not a clique, but this side, V minus V prime is a clique. So this part, in its complement, is a clique, because in V minus V prime in the independent set, no edges, but then in its complement, it has all possible edges. All right. Okay. All right. Now going back to the activity scheduling problem, weighted interval scheduling problem. Actually, it's an independent set problem. So that's why I want to discuss and talk about these things. So this one is really a maximum weight independent set problem. In a graph called interval graph. All right, so what we have is we have a set of intervals. So let me draw an example, okay? So let's see. I think it should be good enough. So let me label them as V1. First, sorry, I1, I2 maybe, not V1 yet. Okay, so I1, I2. This one will be I3, I4. Now, actually, ordering does not matter. If you think about this problem, then ordering does not matter. But let me try follow ordering. Okay. We can construct a graph called interval graph. To model intersection of these intervals or comparability or non-comparability of these intervals. So each vertex, each interval will be represented by a vertex. And we can use VI or II does not matter. Maybe I use V1, V. So maybe use VI for corresponding to interval II. All right. So we have 7 vertices. All right. Now two interval has non-empty intersection, then we add an edge between these two vertices. So I1, I2 intersects, so we add an edge. All right. I2 intersects with I4, so we add an edge. I3 intersects with I4 and I6, we add these two edges. I4 also intersects with I5, I think, right? So 5, 6, 7. I think that's is a graph. I may miss the one edge or two. Yeah, I think that's it. So we get the interval graph. Oh, I find the 6. Yeah, exactly. So I'm right? I missed the 1. All right. Okay, so we get the interval graph. Thank you. So we get this interval graph. All right. Now the problem on this interval graph is to find the independent set of maximum weight. So that's maximum weight independent set problem. So the problem is to find the mutually compatible intervals of maximum weight. So that translates to independent set. Each set of mutually compatible intervals that corresponding to hold on. Okay, that corresponding to independent set, exactly independent set. Weight. Okay, so weight. We haven't put weighting. So suppose they have weight. So let's see. So maybe has 3, 5, 4, 5, maybe 2, 3, 1. Okay. So suppose these are weights are interval. So they become weights on vertices. So here weight will be on vertices. 1. All right. Okay. Now you see it, right? So the corresponding between mutually compatible intervals and the independent sets. So therefore, the problem will really become a maximum independent set problem in interval graphs. Okay. All right. Okay. So let's finish our discussion on interval scheduling problem. So next problem has relation with independent set, maximum independent set. So let's illustrate. I will give you an example of how we do dynamic programming for graphs. So next example is the following. It's related to independent set, but actually it's independent set. But so I formulated it as a vertex cover problem. So the problem is called the minimum weight vertex cover. All right. Now each vertex has a weight. We want to find a set of vertices cover all edges with total minimum weight. All right. So for example, this one, a very simple example. Maybe plot. All right. So if I give you this very simple graph, what's the size of minimum vertex cover? I want to find the minimum set of vertices to cover all edges. So actually 3 vertices will be good enough. This one, this one, this one, right? It cover all edges. Yeah, it's 3. But all right. However, if vertices are weighted, so that may be not the best one. For example, weight of vertices can be, if I put the weights as 1, 1, 1, 1, 2, 2, say 2, 3, 2, or 2, 2, 2 does not matter. Okay. So if I want a vertex cover of instead of minimum size, so here minimum means minimum size. Now instead of minimum size, I want minimum weight. All right. Now the solution, of course, you see it. It's better to use 4 vertices instead of 3 vertices. Also this one. So total weight is only 4. If we use 3 vertices, the total weight will be 7. So it really reduces. So that's our problem. We want to find the vertex cover of minimum weight. The task is find All right. Of course, this problem is very difficult. So we restrict our attention to very special graph, a tree. Otherwise, too difficult. Later on, we'll see why it's so difficult. In a weighted tree. So our graph is a tree. So weight is on vertices, say integers. All right. So that's our example. So that's our input. It's a weighted tree. So let me draw one. So put weight inside. All right. So that's our input. Yeah, negative weight is okay. Yeah, even negative weight does not affect our solution. Yes, that's a method. I mean, the method will still work. All right. Now, because of weight, the problem is getting difficult. If it's unweighted, then it's very simple. If I give a tree, I ask you to find a minimum size vertex cover for a tree. Do you know how to do it? If just minimum size, the graph is a tree, just minimum size vertex cover. Exactly. We never choose leaves. So we never choose leaves. So choose a vertex here, so this will cover these. Then the tree has been reduced. All right. So that's very easy. But now you see this approach does not work. Look at this part. It's better to use leaves. Total weight is only 6. If we use this one, weight will be 8 for these 4 edges. So this idea does not work. All right. Okay, so go back. So what do we do? How do we identify sub-problems and then try to use it to solve our problem? So we are going to use dynamic programming. It's very, very often for trees, we first make a tree to be a rooted tree in order to organize things. So first idea typically happens very often, we make T a rooted tree. To get things organized. It's very useful. That's very easy. We actually pick a vertex as a root. Then the tree will look like this. Once it's a rooted tree, so it has subtrees. So of course, inside each subtree, it has the same structure. We have this kind of hierarchy. So that naturally each subtree can be regarded as a subproblem or subinstance. All right. So first step, make it a rooted tree. Then we have this. Okay. So then what we need to do is just consider a picture like this. So it has subtrees, say T1, T2, say TK. The whole tree is called a T. Then our task is to see how mid-weight vertex cover of T depends how on vertex covers of T1, T2 up to TK. Okay. Yeah, I'm extremely slow now. Okay, but anyway, does not matter. I think we have plenty of time. All right. So anyway, after break, we'll continue. Let's have a break first. All right. Since we are slow, so let's keep it in that way. All right. So see you after break. So try to think about how can we do it. So yeah, perhaps you should think about it. So let's say use which number? normally alpha is not used for this, but let's say alpha of t defined it to be weight of minute weight. Before I stop, I would try to do it in this way. Okay, then you can think about that of t. So suppose we define a value for t as this. Then try to see how can I use it to get a reconciliation for the whole tree and then use dynamic program to compute it. Because it's very natural to view the problem of each subtree as a sub-problem, right? Okay, so try to think about that during break, and we'll continue after the break. All right, okay.